Hello everyone, myself Nabinta Demari, Assistant Professor, Civil Engineering Program, Assam Downtown University. Today I am going to discuss about the pre-stress concrete with bend tendons with you all. Before on the previous videos we have already discussed about the concentric tendons, eccentric tendons, and now today we are going to discuss about the bend tendons. So what are bend tendons, why we need those bend tendons. So and we will also solve a problem basically to find out the stresses, how we can find out the stresses on those kind of bend tendons. So see here, this is a normal simply supported beam. Then this is the tendon which is bent in this form. Here there is a point load here, and we have this is the center CG of the beam here. So we will assume that this bent tendon is at an angle theta from the horizontal. And why we use actually this bent tendon is that because this kind of bent tendons provide an upward thrust. Okay, when they are pre-stressed, they give an upward thrust to the external loadings, and this upward thrust will compensate or counterbalance this external load, and and this will help in reducing the load or the stresses which will be developed. The load will be decreased because this upward thrust is going to counterbalance this load. So the same things will happen here, like only the difference is that on the bend tendons here we will have an upward thrust which is going to counterbalance this external loads. So also this figure here at the bottom, this kind of bend tendons we will for explaining properly, we have to consider the free body diagram of the forces as shown here in this figure. This is the upward thrust 2p sine theta which will be acting and trying to counterbalance this external load. These are the pre-stressing forces which are at an angle theta from the horizontal, and we have the upward thrust 2p sine theta. This upward thrust, because here we will have the vertical components and the horizontal components on both these sides, horizontal and vertical components. So we have here sine theta, here also we have the vertical component to be sine theta, so it is 2p sine theta. The upward force is our 2p sine theta. So now what we are going to do is uh, we know that axial longitudinal force provided by the tendon is how much, p cos theta, where we will see here the axial longitudinal force provided by the tendon is given by p cos theta. Because here we know this horizontal vertical force was vertical component was sine theta, and here also it was sine theta, so we got it to be 2p sine theta, and this was sine. If we write here, this is our sine theta. So we have the sine theta here. These are your longitudinal components provided the tendons. Here we will have longitudinal tendons, axial longitudinal force provided by the tendon to be p cos theta. So this is can be taken as cos theta, sorry, p approximately. Why? Because theta is very much small here, and the direct stress on the section will be how much, p cos theta by a. But since theta is very small, so we will consider it to be p by a approximately. Net, now the net bending moment will be how much. We have the load, this is the external load here, and this is the upward thrust here. So the after compensating or counterbalancing, this load is going to counterbalance this external load. So that will be how much, this w minus, if you do this 2p sine theta, that means this is the total load which is falling on your beam, and this is the upward thrust which your tendon is giving back to this load here. And then when we subtract this two, there are some amount of load remaining, and that load is going to now act here, not like W, it is not going to the entire load. W is not going to act here on the beam, but the after subtracting the upward thrust which is resisting this tendon from the tendon which is resisting this load W, after subtracting that small amount of load will produce the stresses in the beam. So that will be how much? W minus 2p sin theta. See here, the net bending moment will be how much? We know our total moment will be how much. This is the dead load moment, this is the point load moment. So dead load moment will be ws square by 8, we know, and the point load will be how much? The point load now which is acting here, this was our point load. Now after the 2p sin theta, which is the upward thrust, when this acts upwards, what happens? The after counterbalancing there remains some amount of load. That load is your point load now, which will be acting after subtracting, after counterbalancing there will be a load which is acting here, small amount of load, that is a point load. So that the moment of that point load will be WL by 4, and that W is how much? W minus 2p sin theta. So now where dead load and live load. So the extreme fiber stresses will be how much now? The direct stress which is uniform throughout the beam P by A, as well as the net now, the stress due to this bending moment, due to the load, due to this point load and the UDL, we will have plus minus M by Z. So in this way we can find out the for the bend tendons we will find out the stresses. So now we can go with the question. Suppose this is a question here. A pre-stressed concrete beam 400 mm and 600 mm deep has a span of 6 meter, which is this is your span 6 meter, and this is the point load 180 kilonewton here. The beam is pre-stressed with the tendon as shown in the figure. So this is the bend tendon. The external load on the beam consists of a concentrated load of 180 kilonewton. This one, if the effective pre-stressing force is 1200 kilonewton, that means your this pre-stressing force, if I go, this pre-stressing force is how much? 1200 kilonewton. So now that means if we draw the free body diagram, what will happen? This is your UDL 6 kilonewton given to you here, and we have the pre-stressing force to be 1200 kilonewton. Then upward force is 112 kilonewton. This is 6 meter. So at the center if you see it is 3 meter, 3 meter. So now if you have to find out the midsection, if you have to find out on the midsection the upward thrust, upward thrust, the upward stress, the upper stresses, the stresses at the bottom, if you have to calculate what are the stresses that are going to be available here now, the stress due to the pre-stressing force P and the stress due to the bending moment due to this loads. So what is our now, what we have to do, we have to find out the total bending moment, right? This one total bending moment, which is our the stress due to the bending moment due to the dead load, which is 27 kilonewton, and the dead load we know it is dimension is given to us, so we can calculate the dimensions. From the dimensions we'll get the dead load, which is 6 kilonewton per meter. Now we know the net load was how much, so for that we will have to find out what we need. P by A, we need P by A, and also we need what? Plus minus M by Z. So basically the pre-stressing force we know, area we know from the dimensions given to us, Z is our section modulus, which is BD square by 6. So you can calculate, see here it is already calculated here. So Z we know, but the thing which we don't know now is the moment. So moment we have to calculate, and for the moment we have to know the dead loads and live loads. So now what is our dead load? From the dimension it is going to give us our dead load 6 kilonewton per meter. So now due to this dead load there will be a bending moment, so that is WL square by 8. W is your 6 and L is your span 6 meter given to you by 8, so this gives to be 27 kilonewton meter. Now the next load which is going to come on the beam is due to the point load which was here in the question. This is the point load 180 kilonewton. Now we have to find out, due to this bend in the bent tendon, due to this tendon which is bent, that is the bent tendon, due to this which an upward forces will counterbalance and reduce this point load. So now for that we have to calculate the bending, sorry, for that we have to calculate the upward thrust here. So that is 2p sine theta. Now sine theta we can consider it to be 10 theta. Why? Because theta is very very small, so we can consider it to be 10 theta. So 10 theta will be how much in this case? This is your free body diagram here. Now if we see here, this one here, this portion, this this portion, sorry, okay. So if we see this portion, this, so our tan theta will be how much? This perpendicular by base. So perpendicular is how much our, we know from the eccentricity, how much it is given to us in our question. So that is how much? 7 by 150. Okay, this was this one here in the question. It is given, this distance is given to us 160. So that means we can get this value. That means this was how much? This portion was 300 mm. 300 mm. So now 300 minus 160, that will give you your value. Okay, which is, now you know this is the uh, base, perpendicular by base. So perpendicular was 7. Okay. Mm, in the question it should have been mentioned here, 186 meters persisting force. Okay. Yeah. So see here, this is 140, we know, because it was how much? I'm so sorry. So this 300 minus your 160 will give you your this one to be 140. So we have this tan theta will be turned perfectly blue. So this is your 140, and this base is your 6000 mm. That means half of this was 3000. So we can get our 10 here, tan theta. So once we know the tan theta, we can find out our 2p tan theta value, which is 112 kilonewton. Net vertical load will be now how much? Our total point load was given to be 180. So 180 minus the upward force, which is now our 112, we will get how much? 68 kilonewton. So now the bending moment due to this is the point load. Now the ultimate net point load is 60 kilonewton. So we have to calculate the moment will come due to this net load. So therefore the moment will be how much? WL by 4, we know, and L is 6 meter, 4 we know. So now we got the total moment to be 102, which is our bending moment due to the net vertical load, and we have the bending moment due to this dead load. So the total load is this much. Now we can find out our direct stress due to pre-stressing force P by A, and the extreme stress due to bending moment M by Z. And so in the similar way we can calculate the top fiber stress and the bottom fiber stress. Top fiber stress, once you calculate your direct stress and the stress due to bending moment, you will get the top stress to be 5 plus 5.4, which is 10.4 Newton per mm square, and you have your bottom will be 5 minus 5.4, which is minus 0.4 Newton mm square. So that means this is your stress diagram. Here this is direct stress 5 Newton per mm square uniform, and you have M by Z plus minus positive compression at the top and tension at the bottom. So that was 5.4. Now the total stress, which was 5 plus 5.4, 10.4 Newton compression, and here at the small, the bottom portion, we have minus 4 minus 0.4 Newton per mm square of tension here. So this is the final stress diagram, and this is the total stresses at the top and the bottom. The top portion of the beam is in compression of 10.4 with a stress of 10.4 Newton per mm square, and at the bottom we have tension. The beam is undergoing tension here of 1.4 Newton per mm square. So this was your bend tendons, how you can find out the or calculate the stresses in a bend tendon. So thank you for listening to me and solving with me the problem of a bent tendon. See you in the next class. Thank you.